Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to talk about what is called the Central Limit Theorem. The Central Limit Theorem. We need to write this down. And here's why. The Central Limit Theorem is one of the most applicable aspects of statistics, especially as an introductory course. And that is this. Because so far we've been hoping for normally distributed data. Because if we found data that was normally distributed we knew that we could apply the properties of the normal distribution to it. We can find the related probabilities over certain intervals, and it's also handy when we talk about inference and statistical testing. However, not all data is normally distributed, so you'd think that might cause a problem. Well, the problem is fixed right here by the central limit theorem, and what I hope to do today is I hope to develop the concept for you of why it works and where it comes from. So this is not a mathematical proof, this is just a derivation of the idea. So let's take a look. The central limit theorem. And to take a look, we're going to begin with a data set. How about the data set 2, 4, 6, and you know what? How about an 8? Let's just give it an 8. 2, 4, 6, and 8. So let's draw this. Let's graph it. Graph as a histogram. I know we haven't made a histogram in a while, but let's try one. So I'm going to make my vertical axis will be my frequency. Horizontal axis is going to be my data. So let's see, here's 1, 2, 3, 4, 5, 6, 7, 8, and we'll just go out to 9. I'm not sure if I'm going to need it, so this is my data. And I should probably move that down a little bit. 1, 2, 3, 4, 5, 6, 7, 8, 9. And my frequency, let's put our frequency, we don't have to go very high, do we? 1, 2, that's plenty high, that's probably too high. 1, 2, because each data value only occurs once. Now, if I have a data value of 2 and I have to make class boundaries so they're continuous, that's going to give me a class boundary that's going to look like for 2 will be from 1 to 3, and then from 4 to get 4 it'll be from 3 to 5, and it's going to create all of these that just come across, and I think mine is going down. Yours should be perfectly horizontal. There, that's it. That's my distribution. Now from that distribution, what I'd like to do is let's take a moment and let's find both the mean, the variance, and the standard deviation. So the mean of this, the mean, mu, is, and we're going to assume that this is the entire data set, not a sample. So the mean would be 2 plus 4 plus 6 plus 8. And take all of that, we're going to divide it by the number of data. We have 4, so let's see. 2 plus 8, that's 10, plus another 10, that's 20. Divided by 4. Now I'm coming up with a mean of 5. You should check me on that, and if I get something different, let me know. Now, speak up. The variance. The variance is, now remember we take our data. So our first data value was a 2. And then we subtract the mean of 5. We square it. Plus our next one was 4 minus 2, square it. Plus our next data value, 6, minus, oh, I made a total mistake. You should have said something. 4 minus 5, the mean, there we go, squared. Plus the next data value for 6 minus 5, squared. Plus our last data value of 8 minus 5, squared. We take all of that, divided by the number of data, that's 4. So let's see, this is going to be equal to 2 minus 5 is negative 3. Let's square that. We get a 9. Plus 4 minus 5 is -1. We're going to square that and get a positive 1. And then 6 minus 5 is 1. Square it for 1. 8 minus 5, that's 3. Square it, that's 9. Add all that up. Divide it by 4. And it looks like we get 20 again. 20 over 4. So our variance is 5. So what does that mean? That means that our standard deviation, well, that's the square root of the variance. Well, that's the square root of 5. Now, in the event that you are tempted to put square root of 5 into your calculator and turn it into a non-terminating, non-patterned decimal, don't. Just leave it as the square root of 5. You'll be much happier, I promise you. Now, we're going to do something that's, I don't think it's obvious, but we're going to do it anyway. What we're going to do is we are going to take all possible samples of size 2. So that may seem a little vague, but it'll make sense in a moment. So what we're going to do is I'm going to denote it as a sample. So we're going to make a little table here. We'll take our sample. And we're going to, we'll just write it this way. Make a little table, and then we're going to have x bar, the mean of those samples. And we're going to have to take a lot of them, so we might need 2 columns. How about that? Sample. X bar. So, for example, I could sample a 2 and then a 2. Now, I'm just, imagine we have our data values of 2, 4, 6, 8. Reach into a jar, pull one out, you get a 2. Put it back in, reach it out, pull it back out. What do you get? Another 2. So one of your samples would be 2, 2. Another one would, now I'm going to be very systematic here. Another one would be, well, you first grab a 2, then maybe you grab the 4. Then you grab a 2 and a 6. Then you grab the 2 and then the 8. And then maybe I'm going to need some space. Hopefully this fits. Now maybe let's start with the 4s. Maybe you grab a 4, then a 2. 4 and a 4. 4 and a 6. And finally a 4 and an 8. Okay, let's keep going. And we'll use our next column. Now maybe you draw a 6 and a 2. Then a 6 and a 4. And then you draw a 6 and a 6. And then a 6 and an 8. And then you draw an 8 and then a 2. And then an 8 and a 4, an 8, 6, and finally an 8 and an 8. And those are all possible samples of size 2. Now, I'm going to make an argument as to why this makes sense. Because I think it does, and I think we naturally do it. For example, if you talk about sports, what do? You represent their performance by some kind of an average. For example, you say that the player, maybe a baseball player has a batting average of 300. Well, what does that mean? It means that player hits 3 out of every 10 times the player is at bat. It doesn't. Now, here's what it doesn't tell you, though. It doesn't tell you when they made a hit. It means to get a hit, it means they could have gotten a single, a double, a triple, or a home run. But you don't know that. You don't know anything about that. So you're just representing that batter's hitting record with an average. You know nothing about singles, doubles, triples, and home runs. So it's a natural thing to do to represent some kind of a performance based on an average. For example, if you were to talk about basketball teams, you might say, oh, the average height of an NBA men's basketball team is 6 feet 6 inches. Well, does that represent every player? No. Is every player 6 feet 6 inches? Probably not. That means some are taller, some are shorter. Few might be 6 feet 6. But the average is what we represent the team by, or the batting average is what we represent the hits by. So I'm going to do the same thing. I'm going to represent my samples by their average. So now we're going to to find the average of each of these, we just add the two numbers, divide by 2. So 2 plus 2, that's 4. Divide it by 2, we get 2. And let's keep going. We're going to get a 3, a 4, a 5, a 3, and I'll stop here. 4 plus 4 is 8. Sorry, I did that kind of fast. That probably wasn't fair. 4 plus 4 is 8, divided by 2. 4 plus 6 is 10, divide that by 2. 4 plus 8, that's 12. 12 divided by 2 is 6. Okay, we're on the second column now. 6 plus 2 is 8. We divide it by 2 for 4. 6 plus 4 is 10. Divided by 2 is 5. 6 plus 6 is 12. Divide that by 2 for a 6. 6 plus 8. 6 plus 8, that's 14. Divided by 2 is 7. 8 plus 2 is 10. Divided by 2 is 5. 8 plus 4 is 12. Divided by 2 is 6. 8 plus 6 is 14. Divided by 2, 7. And then 8 plus 8 is 16. Divided by 2 is 8. Okay, that's 8. Now, instead of having 16 different samples, let's regroup what we've got. So we're going to make a little frequency distribution. So we're going to put our x bars over here. This is our means and our frequencies. Mean and frequency. So let's see, what are our means? Well, my smallest mean I've got is a 2. Oh, I've got 3. What else do I have? Oh, I have a 4, 5. Let's see, do I have anything bigger than 5s? Oh, down here in the bottom of the first column, I have a 6. Anything else? Oh, there's a 7. And, oh, the last one was an 8. Now, take a moment and go through, and I'm going to do this too, but count the frequency for each mean, each sample mean. I need to be very careful, each sample mean. So for example, the sample mean of 2 only appears once. But let's see, how about 3? What about 3? Let's do these together. What the heck? 3, there's a 3. Oh, and here's a 3. So it looks like the sample mean of 3 has a frequency of 2. Let's do another one. How about 4s? 1. Oh, here's another one. 2, 3, and that's it. So we've got 3. The sample mean of 4 occurs 3 times. All right, let's do another one. 5s. Here's 5, 2, 3, 4. Oh, I'm getting 4 on that one. That's a big one. 4. And then let's grab another color. Let's just keep it up. So we got 6s next. 6. Ooh, that's not a very good color. It's very hard to see. How about 6? There we go. That's better. 6. That's 1, 2, 3. Looks like I have 3 6s. 7s. Let's see. There's a 7. Oh, and right down there, another 7. There's 2 of those. And then it looks like finally I just have this last 8 for 1. Now, here's what I want to do. I would like to take and make a histogram on top of my original histogram using this data set. So here we go. So notice now I have my data is being represented as their averages. So above 2, I have a frequency of 1. Oh, I'm gonna have to make all sorts of modifications. I'm going to go all the way up to 4 here. 3, 4. So at 2, I'm going to put a little dot here. At 2, I'm going to go up to 1. At 3, I'm going to have to go all the way up to 2. Then I'll put the bars in a moment. Because notice now my data is 2, 3, 4, 5, 6, 7, 8. So my boundaries are going to be 1.5 to 2.5. So let's do that. So let's do this whole picture in this orange. So blue. So it offsets. So from 1.5 to 2.5, from 2.5 to 3.5. And then, let's see, my next data value, 4, has a frequency of 3. So that's going to be from 3.5 to 4.5. And then my next data value of 5, wow, that's the big frequency there. That's the big one. That one goes from 4.5 to 5.5. And then what do we have? 6 goes back down. Goes back down to a frequency of 3. So that's going to be, carry that over. So it's going to go from 5.5 to 6.5. And if we do it again, 7 has a frequency of 2. And then 8 has a frequency of 1. Whoa, what just happened here? A lot just happened. A lot just happened. Okay, look at what just happened. And as a matter of fact, I'm going to take... goodness, this is just so pretty, but I'm going to need another page. So let's go to another page. You ready? I'm going to go to another page. I'm going to turn this page off. Actually, before I do that, I'm going to stay on this page and let's make a note. No, I think we can do it. Let's just go to the new page. So turn this one back down. Okay, so let's write what just happened. Notice, originally we had a uniform distribution. Notice we began with a uniform distribution. Meaning it's just flat, boring. Distribution. Then we take all possible samples of size 2 and create I'm going to put what appears, or what seems. We create a normal distribution. Whoa, a normal distribution. Now, if that's really what just happened, that means that all that work that we've done about the normal distribution, we can apply to that uniform distribution if we're talking about groups withdrawn from that. So let's go a little further. This is getting good. So I'm going to go grab my frequency distribution here. I'm going to go grab that frequency distribution, and I'm going to copy it right there. Because you know what I want to do is we want to copy, paste, and hopefully it's there. Oh, it is. Look at that. So the other day I tried this and it did not work so well. So I feel very happy. Success. Okay. There's my frequency distribution, but we need to do some work. I want to remember that originally we said that our mean was 5. Our variance was 5. And our standard deviation is the square root of 5. So I'm just recording those. Now, let's do this. Let's do the same, but for this frequency distribution. All right, so here we go. So we're going to calculate. Now, I'm going to use this different notation. We're going to calculate the mean, but what are we calculating it of? We're calculating it of the x bars. It's the mean of the sample means. Oh, that's a good vocabulary word. The mean of sample means. Okay, so here we go. Well, let's see. Our first data value is 2, and it occurs once. Plus, we have a 3, and that occurs twice. Plus, what else do we have? 3. We have a 4, and that occurs 3 times. plus we have a 5. And that one, oh, that was our big one. That happened 4 different ways. Plus a 6. That was a 3. Occurred 3 different ways. Plus 7. That occurred twice. Plus the 8, which occurred the 1 time. But now, remember, previously we divided by 4. But if you recall this frequency, if I add this up, this is a frequency we went from a data set of 4 now to a data set of 16. So we have to adjust our denominator as well. So this is going to be a 2 plus 6 plus 12 plus 20 plus 18 plus 14, oh goodness, plus 8. Let's see, divided by 16. Oh, look at it this way. This is, if you have a calculator, you should help me out or double check me. But I think I see the pattern. If you look from the outer edges, the 8 plus the 2 is 10. The 6 plus the 14, that's 20. That gives me a total of 30. 12 and 18, that's another 30 for 60 plus the 20. I'm coming up with 80. 80 over 16. But wait a minute, that's 5. That's 5. Wait a minute. What weird, the mean of the sample means is the same as the mean. Okay, that's the first point. Second point, well, let's find the variance. Let's find that variance. The variance, I'm going to scoot over here. The variance, well, remember, we take the data. So the data was a 2 minus the mean of 5, square it, and we multiply it by its frequency. Plus 3 minus 5 squared times 2. Plus, I'm going to put all of this in brackets. This might save some space. Plus 4 minus 5 squared times, this occurred 3 times, plus 5 minus the mean of 5, square it, multiply it by its frequency of 4, plus 6 minus 5 squared times its frequency of 3, plus 7 minus 5 squared times its frequency of 2, plus, we're almost there, plus 8 minus 5 squared times its frequency of 1. And then we're going to divide all this by the number of data, which is 16. So this is going to give me 2 minus 5 squared. Or 2 minus 5, negative 3. Square it, 9. So I'm going to get a big bracket here. I'm going to get a 9 plus 3 minus 5 is negative 2. We square it for 4, multiply it by 2 for 8. Plus 4 minus 5 is negative 1. Square it for 1, multiply it by 3. Plus 5 minus 5 is 0. Square it for 0, multiply it by 4. And I'm going to just record the 0 just so we keep track. Plus 6 minus 5 is 1. Square it is 1. Multiply it by 3. Plus 7 minus 5 is 2. Square it is 4 times 2 is 8. Plus 8 minus 5 is 3. Square it for 9 times 1 is 9. Divide that by 16. Okay, now this is where we have to be. We have to be by design. We're working by design. So I'm going to try to lead you here. I'm going to add these up. 9 plus 8 is 17 plus 3 more is 20. But then I have another 9 plus 8 plus 3 on the other side. So this is really 40. I'm going to write this as 40 over 16. Now, we haven't been reducing fractions a lot, but I think it's time. Let's write this as 8 times 5 over 8 times 2. Well, that's just 5 over 2. Now, at that point, you might be happy. You might say, hey, look, I've got my answer. I am done. But that's not the real point here. This is the point. That 5, have we seen that 5 before? That 5, oh, that 5 is this 5. I'm going to grab a yellow for this. We'll look up in the upper right part of the screen. It's that 5 right there. So wait a minute. What we just found is that the variance, oops, my notation was off. The variance of the sample means is equal to the variance of the original problem divided by, now it's got this 2. Where in the world have we seen this 2? Well, remember what we did? We took samples of size 2. Yeah, that's the same 2. And so we say that's n. N is the size of the sample. Size of samples. Whoa, so there it is. So the variance of the sample means, is equal to the original variance divided by the sample size. And if we go one step further, we could say that the standard deviation of the sample means is the square root of all that. Well, it's the square root of the variance over n. Well, the square root, remember you can break it up into the square root of the variance over the square root of n. But the square root of the variance, that's the standard deviation, divided by the square root of the sample size. And this is called often the standard error. The standard error of the mean. And what have we learned? Well, at this point, the crowd would be going wild if this was an action film, because we have just found that we can take any data set. It doesn't matter how oddly shaped it is. But if we take all possible samples of size n, then we know that we can treat it as a normally distributed data set. And by doing that, that allows many of the different tests that we use in statistics today. So I think we're going to stop there. In the next video, we're going to re-summarize all of these properties, and we're going to look at some problems. I hope you enjoyed that development. Thanks for watching.